Section 16.6 is on page 1022. It talks about surface integrals. We just found surface area in the previous section. Now we're talking about a surface integral. What's a surface integral? Surface integrals, which is this section, to surface area like the previous section, is much like line integrals, which is 16.1, to arc length in 6.3, the last class. Note surface integrals and surface areas are the same if you see that right there, the double integral. This is the formula for surface integral. It's really this. If you set that equal to 1, then that's pretty much the previous section. We did something like this back in the days. If you take a single integral and you write a 1 in there, that's length. If you take a double integral and if you put for the function 1, that's area. And if you take a triple integral and you put a 1 in there, that's volume. But if you take a single integral and give it a height, that single integral becomes an area. Right? A bit confusing, but the difference between what we did in the last section, this was what we did in the last section. Now what we're doing, we're adding a function, and we'll talk about what that means. The book has a lot of extra examples. You could look at the very beginning of 16.6. Surface integrals allow us to compute the mass of a surface, the flow of liquid across a membrane, and a total electrical charge on a curved surface in space. Right? Not necessarily a specific area. And previously we found the area of that curved surface. Now we're trying to figure out how much are we accumulating within that within that curved surface. Meaning, if we have energy flowing straight up, this, even though those have the same area, this will accumulate a lot more than this. So taking the shape into account, that's where this comes in. If g of xyz gives the mass density at each point on a surface S, then the total mass is calculated by this. And it comes down to really one of two things. Am I given the description of the surface in terms of a vector? I'll use the following. This is nothing more than g of f of r, so to speak. And here, if I'm given z equal f of xy, that would be the actual formula. I do want to know, you could be given y equal a function of x and z, and that will become f sub x squared plus 1 squared plus f sub 1 squared. I derived that in the last section. I derived it in z equal. I could have derived it in terms of any of those other functions. You could adjust accordingly. Now let's look at some examples. I look at page 131. Integrate the given function over the given surface. It says g of x yz is g of x over the cylindrical surface. I'm going to do this problem two ways. Only this problem two ways. So x squared plus z squared equal here it is. Assuming this is 4, and let's say this is 1, right? So, if I want to figure out what the surface integral is, well, I'm going to do this two ways. One way, I'm going to start using this blue color. I'm going to say, well, let's say r of x and y is actually x, y, and let's see, if I want z equal 4 minus y squared, square root of z is bigger than or equal to 0, so it's really half of this, right? It's the upper half, minus the, just the upper half of this. Okay, now I see. So, I could could say the square root of 4 minus y squared. And I could say here we have x varying between -1 and 1, and y varies between -2 and +2. True? Yeah, that's as far as I can go left and right. So how does this work? Well, according to what we know, the double integral over s of g of x, y, z in this case, d rho, that is the integral from, oh boy, I meant 1 to 4, right? You guys forgive me, right? dx, the integral from -2 to 2 dy. And let's see how this works. What I need to figure out on the side, I need to figure out, well, what's r sub x? That is 1, 0, 0. What's r sub y? That is 0, 1, 1 over twice the square root of 4 minus y squared times -2y. Right? So if I take the cross product of those, of course, you could use u and v if you want right here. It doesn't really matter. So here, I'm looking at the I that is 0 minus 0, that turns out to be a 0. And the j, that turns out to be negative y over the square root of 4 minus y squared. And the k, that turns out to be just a 1. So if I take the magnitude of that, that would be the square root of y squared over 4 minus y squared plus 1. That would be the square root of y squared plus 4 minus y squared over 4 minus y squared. That turns out to be a 2 over the square root of 4 minus y squared. So this is going to be right here. 2 over the square root of 4 minus y squared times g, and what's g? Z. What's z? The square root of 4 minus y squared. There it is. That's the difference between the previous section and this section. Only the right portion. You notice that those cancel out. I'm left with a 2 times, well, what is that? Isn't that a 4? And isn't that a 3? And what is that altogether? A 24 altogether? There it is. Done. Now, I'm going to do this problem a different way. This is the only problem I'm going to do 2 ways. Or I could say the double integral over s of g of x, y, z, d rho is the integral. And I could say from 1 to 4. I could say from -2 to 2. That's not a problem. Now, I know that this is the square root of 4 minus y squared times the square root of, and let me go on the side and figure out actually right there. Instead of doing the vector, you know how I find the vector right there? Instead of doing that, I could say, you know what? Let's take the square root of f sub x, that is 0 squared, plus f sub y, that is 1 over twice the square root of 4 minus y squared times -2y squared plus 1. And notice, those are the same. There's no need for me to do this, take r sub x, r sub y. If I was given the function in terms of a function, then I should really use this formula. That's a lot faster than this. And do you notice that when I plug this in there, I'm going to get exactly what this is, and I continue on? So, I'm just showing you. You could do every problem both ways. There's no point in doing that. This is just a waste of time. If I'm given my function in terms of r of u and v, I would use that, and I'm done. No need to cross over. Alright? The next problem. This is the function over the cone. A cone z equal x squared plus y squared square root, one of those. And I want this to run from 0 all the way, assume that's a 1 right there. Right? So here, the problem is I could keep it in terms of z. That's not a problem, right? The problem comes up when I want to describe this in terms of x and y. We need two unknowns. So do you notice when I write a double integral, I'll have a problem writing the limits because I need x is varying and y is varying. So instead, I could say, you know what? I could say let r of u and v be u the cosine of v, u the sine of v, and isn't this z equal r squared square root? So I could say u. You could leave it in terms of z and I mean r and theta if you wish. Just want to separate between this and polar. So here I could say let v vary between 0 and 2 pi, and let u vary between 0 and 1. And that's going to take on all of that value. It's going to take all of it, the whole surface. And now I could say, well, since I did figure this out, let me take r sub u, that is cosine of v, sine of v, and a 1. R sub v, that is negative u, the sine of v, u, the cosine of v, and a 0. And if I take r sub u cross with r sub v, we did this already, and we're going to do this over and over. That's going to be 0, that's going to be negative u, the cosine of v, the j0 minus, it's going to be u, the sine of v, and that's going to be u cosine squared of v plus u sine squared of v, right? So this is u, and if I take the magnitude of that, I'm going to get the square root of u squared cosine squared of v plus u squared sine squared of v plus u squared, oh, my handwriting is getting worse, u squared cosine squared of v plus u squared sine squared of v plus u squared. While you factor out a u squared, that's u squared plus u squared, square root of 2u. So the double integral over s of f of x, y, z is going to equal the integral from 0 to 2 pi, the integral from 0 to 1, and I'm going to run, let me see, dv du, and this is going to be the square root of 2 times u, and what's z in this case? A u minus u cosine of v, and there it is. And on number 14, there is G, whatever G is, that's the surface, but over the surface cut by the cylinder, and x runs between, let me see, 1, 2, 1, 2. It's supposed to be infinite, right? Z equals 0, so it runs from 0. X is between 0 and 1. Something like this. So, if I look at this, I notice that x runs between 0 and 1, and y runs between, if I put a 0 right there, y runs between negative 4 and 4. Right? So this region is actually this region, and the double integral of g of x, y, z, d rho is going to equal the integral. X is going to run from 0 to 1, and y is going to run from negative 4 to 4, dy dx, and it's going to be x square root of y squared plus 4, and what do you think is going to go right there? And that would be the f sub x squared plus f sub y squared plus 1, and there's the home.